Okay, so you'll probably notice that I did put up a practice exam, right? And right there up on Carmen. I did have a question. Someone, more than one person, emailed me asking me where to find the videos. So in case you were one of those people and didn't see my response, or just were one of the people who couldn't find anything and was too embarrassed to email me, right? If you basically just come up to the home and then scroll down, right? Everything's sort of organized in these modules. So though, starting tomorrow, there'll be a new module down here, steel, right? And it'll have all the same stuff, right? So this page just has a link to all the recordings. So the midterm will cover the first two modules, right? The fundamentals of physical metallurgy and aluminum and alloys. So I labeled it a practice exam, but it's not really a practice exam so much as it was actually just the exam I gave last year, right? So you won't see these questions, but it will be along the same format, right? So I like to give a couple short answer questions, right? Which can be answered in less than a paragraph or a couple quick schematic drawings, right? If you find yourself writing a full page for these short answers, you're going way too deep, right? I said 1 or 2 paragraphs, but really 1 paragraph, a couple sentences, right? Or some schematics. And you have to answer 3 out of the 4, right? I generally give a choice as to what ones you want to answer. And then there'll be a long answer section where you have to answer 2 out of the following 3, right? And these are more in depth, right? So these questions are essentially worth 30 points each, right? And generally, the key to all this, and as I'll be going through when I go through the notes today and pick out the highlights, really the key is relating everything back to structure, properties, processing, right? That is the key fundamental concept of material science as a whole and physical metallurgy in particular, right? Composition you can think of that as like the genetics, right? And the processing is all the metagenetics, the epigenetics, right? Right? I can't change my genes, but if I exercise more, I wouldn't be as fat or out of breath, right? Right? That I can change, just don't, right? That's my processing. If a lot of the questions are going to be relating how does the genetics relate, the composition, right? Composition is going to tell us what phases are possible, right? My genetics tell me I am not going to be a basketball player, right? I can't change. There's nothing I can do about my height, right? Then looking at processing, right? Processing is going to tell us out of the whole possible space of structures and properties, which ones we actually have, which phases are going to be there, right? Whether I quench from a high temperature or quench from a low temperature, whether I age for a long time or a short time, right? I'm not changing the composition, but I am changing the microstructure and the properties. So when going through the notes and thinking about the exam, That's the stuff I want you to focus on, right? Don't memorize. There a lot of details you don't need to memorize, right? You do need to know what are the precipitation sequence for aluminum copper, right? I don't expect you to remember the crystal structure of the phases, intermediate phases, and other alloys, and other, right? That's a task in memorization, right? The exam is looking to test your understanding of key physical concepts, right? Not understanding what exactly you mean by a particular heat treatment, right? Right. So if you look at the questions, they generally start out with a pretty basic concept. In this case, I said the more an aluminum alloy is dependent on precipitation hardening for strength, the lower the value of the ratio between fatigue and tensile strength, right? Which means that we can increase the strength in an alloy, but we don't have as much room to introduce the fatigue strength in a precipitation hardened sequence. Well, why is that? Because the same precipitates that give us high strength also cause us localization of plasticity once we do start to yield. You get softening and have a natural persistent shear band, which is going to kill your fatigue life, right? You'll just constantly keep ratcheting back and forth on that same slip plane, and every time you do it, you're going to make your particles smaller and smaller until you dissolve them away. Then you have no strengthening there, right? The second question, right, is looking at Hall-Petch. Why is Hall-Petch low in aluminum and high in iron, right? I guarantee you're going to have something that's going to relate to the high stacking fault energy in aluminum, right? And its relation to strength, right? And strengthening in some way, shape, or form, right? That's a guarantee. You're going to see that on the exam, right? Right. And then, the third option was explain the precipitation sequence from GP zones to the thermodynamically stable phase in an aluminum alloy of your choosing, right? Maybe you had an internship and you worked with aluminum mag alloys, so you know that system better, right? But almost everyone did aluminum copper last year because that's the classic one that we spent a lot of time on. But they're all about microstructure processing and properties. The other thing to keep in mind is when I'm grading your exam, I'm looking for excuses to give you points, not excuses to take away points, right? So if you think you might know, write it down, right? Give me a reason to say, oh, it's not exactly what I was looking for, but they did learn this other thing that was important. I can give them some credit. Right? I'm looking for ways to give everyone points. Right? And for the grad students who had me, you know that people do well, right? I like people to do well, right? And I like to give people the benefit of the doubt. So let's take a little bit of time and go through and hit the high points. Okay. Right. So I think this first slide is pretty instrumental. We spent a lot of time talking about what we can see from this, right? what is the structure of a polycrystal, right? Why are these colored different, right? Because there's an orientation difference, right? We can see that grain size is not super uniform, right? Even when it's a well-annealed structure with equiax grains, right? We see that grain boundaries are generally straight, and our grain boundary and our triple points tend to make 120 degrees, right? If we saw a grain boundary that deviated significantly from 120 degrees, we might speculate that one of the grains that met at that triple point was some kind of special energy with either a lower or higher grain boundary tension than others. So there's a lot we can tell by looking at this structure, right? Sort of a dislocation model, right? Again, don't need to know the structure, but we can think of a low angle grain boundary as being made up of an array of dislocations, right? And that as we increase the angle or the symmetry, the structure becomes pretty complicated, and we rapidly lose our ability to describe the grain boundary, right? We talked about crystal orientations, right? You don't need to memorize any of these definitions, right? It is important to know we need 3 parameters to define a misorientation, and another 2 parameters to give us a grain boundary normal. So that's the 5 parameters we need to describe the grain boundary, right? As far as stress field near a grain boundary, you just need to know that they're very small. They're much smaller than the stress field of an isolated dislocation, right? Do not force yourself to learn this derivation. You won't need it, right? All right. The energy of a dislocation, GB squared, right? Proportional to GB squared. Right? And understanding stable and unstable grain boundary configurations, right? The tensions of the interfaces. I did mention wetting versus making discrete particles, right? That was a homework question, right? And the difference between, I would say, a coherent and an incoherent interface, right? And again, big concepts are much more important than specific details, right? The difference in energy, the Poisson's ratio effect, term that comes in between a screw and an edge is not super important, right? But a general. So in terms of strengthening, right, what are the only things we can do, right? What is our total toolbox for making metals stronger, right? We're trying to increase the number of times our dislocations hit obstacles. So what obstacles do we have to play with? Right? Solid solution strengthening, we can put in more solute. We can put in second phase particles. We can put in more dislocations, or we can make the grain smaller and effectively put in more grain boundaries. That's it. We got 4 knobs we can turn. Right? And which knobs we have available to us depends on the composition of our system. Okay? You should know what the pyral stress is, right? And generally, it's going to be higher in BCC and HCP than in FCC limits, right? Right? The force always acts perpendicular on a dislocation, and the general form for the line tension of a dislocation. Why is the line tension important? Well, because this is what gives rise to our interaction, a way we can analyze our interactions, right? If we go into a particle with a lower modulus, the line tension of our dislocation as it's cutting through the particle is reduced, right? And that's going to give rise to a resisting, right? The dislocation is going to want to stay there, right? If it has a higher modulus or a larger Berger's vector, it's going to have a more tension. We're going to need to put a lot more energy into it to get it to pass in. But once it's in, it's going to want to come out. All right. Dislocations are not often full dislocations, they're partials. For aluminum, this is important because the high stacking fault energy means those partials are close together. It means they can come back together easier to cross-slip. All right? Whereas in, say, nickel, with a lower stacking fault energy, those partials are going to be farther apart. Right? Planar versus wavy slip. Right? This was a quiz question I asked, right? Right? Kinking, dislocations don't move uniformly. They move in jerky steps, right? This was actually a big central focus of historical focus of this workshop I was at. I was looking at sort of the advances that have been made in modeling the mechanical behavior of polycrystals over the last 50 years, both in metallurgy and geological materials, right? Because rocks are crystals too. They do the same thing that metals do, but they just do it on much slower strain rates and much longer timescales. Right? So whereas we can consider a strain rate of 10 to the minus 3, like we would do in the tensile test, they consider strain rates of 10 to the minus 12, 10 to the minus 13th that you get from geological timescales, but it's still dislocation moving through crystals. But one of the things was a key concept to understanding the field was understanding that dislocations don't move. They're not like cars on an open expressway. They're more like cars in New York City. They move in tiny little discrete chunks of distance before, right? And they can't all move at once, right? So they have to produce they produce kinks. Okay? Right? So work hardening, right? The Taylor relationship, square root rho. Right? Dislocation, intersections produce obstacles. The more dislocations we have, the more obstacles we have. Right? Okay. Cell structure, important later, not so important for this exam. All right. Hall-Petch effects, right? It's not, you don't need to particularly memorize or learn the sort of the factors for grain boundary strengthening. Just that FCC metals tend to have a smaller Hall-Petch effect than BCC or HCP. Right? But everyone knows what the Hall-Petch effect is. Solid solution strengthening, right? Your ideal case is going to be a more compliant atom that has a biggest possible size difference, right? You want changes in modulus and changes in size. Orthogonal distortions are not at all important for aluminum. They are important for steel. So we've got the size effect and the modulus effect. And then particle strengthening, what are the differences that we have to consider, right? And again, there's expressions here. Forget these. You don't need them. Don't even bother to write them down, right? They're not important for the exam. What is important to know is that coherency has an effect, right? What's easier to cut? A coherent interface or a incoherent interface? Coherent interface, because you've got everything's nice and well aligned, right? But it gives rise to a strain field. That strain field interacts with the dislocations, right? That's GP zones in a nutshell, right? Right? Modulus hardening. As I cut through, I change my local modulus, which is going to change my line tension. Right? That's what's important to know, not this relationship. Chemical strengthening, generally a big effect or a small effect? Generally small effect. How can we make it a big effect? Either make your particles very small so that the incremental amount of surface energy or surface area that you add by making a step is large, or make that step large by passing a lot of dislocations to it, right? But as you do that, you're also reducing your effective precipitate size. So it's pretty safe to say chemical strengthening is going to be the weakest effect, right? Order strengthening, we don't need to worry about this too much in aluminum, except in the equilibrium phases, but those aren't of technological relevance anyway, right? So are you likely to see a question on order strengthening in aluminum on the exam? No, right? You might see that I might ask you a question about whether it exists, right? What are the main mechanisms behind particle strengthening? But you won't see it in connection with an aluminum alloy, right? You definitely will in nickel, right? Because the strengthening phase, gamma prime, is an ordered structure, and this is one of the primary strengthening mechanisms. But for aluminum, we never see it because we're not interested in those phases. We're interested in the fine dispersion of intermediate phases for the most part. Looping, and then the peak is generally where looping and cutting, those strengths intersect, right? Because if I make my particles any larger, it becomes easier to bow around them. If I make them smaller, it becomes slightly easier to cut them, right? In terms of aluminum, am I in the right folder? Oh, it's because I'm looking at the wrong year. I was like, I knew I updated those notes. Okay. So, you should know the general properties of aluminum, right? Make a note on your sheet of the lattice parameters, right? You should know that it's all FCC at any reasonable combination of temperatures and pressures, right? There are high pressure phases, but they're not quenchable. So as soon as you release the pressure, it goes back to FCC, right? So since we're not designing structures to withstand hundreds of gigapascals, we don't care about it, right? Right. It's good to know some properties relative to some other classes, aluminum versus steel and titanium. All right. Okay. So, big key idea with aluminum is that aluminum does not have appreciable solubility with very many elements. Right? So what does this mean? Right? So we don't have a lot of main alloy systems to focus on for aluminum. Right? And we have to worry a lot about impurities. So very small concentrations can give us secondary phase formation. These intermetallics are typically brittle and destroy properties if we allow them in too much. Sometimes they can help, like with fatigue resistance in aluminum copper alloys, right? A little bit of intermetallics, if we can get them to nucleate homogeneously, breaks up our slip, right? Right? And basically because of this, a lot of our alloys are precipitation strengthened. Okay? We spent some time looking at the common tangent construction, right? It's always good to understand this, right? But I'm not going to explicitly ask any questions on it, right? Right? But being able to internalize this could help you potentially with other questions, right? If I ask about like that question with the precipitation sequence in other in an aluminum system, you can put I guess it's a little farther ahead. Right. Thermodynamics of nucleation, right? This is a very useful, you should be able to, everyone should know this diagram, right? And understand the physical meaning of delta G star and R star and what goes into it, right? And why we need undercooling, right? This was, you're not going to see that exact same question, but I thought it was an important enough concept to ask an exam question on it last year, right? So that should be a key that I think it's kind of important. Okay. Right. What are GP zones? Right. What's going on here? Anytime I ask a rhetorical question in the notes, that's probably a good clue too. Right? Why does it saturate here? And then why does it start again? Right? GP zones grow, right? And then we start nucleation of secondary phases. Right? In this part, our structure isn't static, but our strengthening is saturated. Right? We're still evolving. I'll explain that a little bit later on. Okay? Right, this is just the definition of Ostwald ripening. Right. Right. This concept of centers of strain, right, for GP zones, right, and that when the GP zones are small, it's impossible to be, right, we can't bend our dislocation around all of these small GP zones, so we naturally have to cut through them. And going from a center of strain to a low strain region is easy. Going from a low strain region into the center of strain is hard, right? But since we have roughly equal numbers, we don't have a whole lot of strengthening. But when the particles grow, and we can lie in low strain regions, now we get more strengthening out of this. Because everywhere on the dislocation is going from easy to hard. Right? We don't have parts going from hard to easy. Okay. Why do GP zones take the shape they do? Right? And why are they different shapes in different systems? Right? It's all about the elastic strain and the coherence. Right? If we're more uniform in size and in elastic compliance, such as aluminum mag versus aluminum copper, we'll get round GP zones because we're altering our balance between surface energy and elastic strain. Here, right, we could adopt a lower surface energy by making this a sphere. But in this case, we generate plates because it aligns the distortions with our directions of elastic anisotropy in the aluminum, right? Reducing our overall strain energy. Okay. Cutting, that's exactly the same as what we said before, right? So, like I said, for the question about transition phases, right? If there was a similar type question asked, one way to write this is by doing a sketch like this, right? Even though the overall free energy change is less, we go from G0 to G1 by nucleating GP zones rather than all the way down here, right? We still get a drop and we only have to change our composition from A0 to A1 in the matrix rather than going from A0 to A4, right? There's a lot more diffusion that has to happen to get to our equilibrium phase, right? Then we can talk about the coherency effects, right? And how R star and G star for this is much, much larger, right? So basically, this picture and this picture, right? These are good schematic representations of the process. Okay? I do not expect you to know the crystal structures of these intermediate phases, right? You can look that stuff up. Right? General trends that you get less coherent and bigger unit cells as you go from the intermediate phases to the equilibrium, right? Role of vacancies. I spent a lot of time on this, and there wasn't a question on last year's exam on it. Might be a good one. Right? So, vacancies and precipitate free zones. Right? Especially linking it back to something like this. Right? What happens if I don't have a critical supersaturation of vacancies? And then being able to interpret these sorts of things, right? So understanding what's going to happen if I do quench A1 versus A2, right? Well, A2, I'm below the GP zone solvus, right? So that's what I'm going to nucleate out. Up here, I'm well above the GP zone solvus, right? So chances are I'm going to nucleate a equilibrium phase or near equilibrium phase, right? GP zones nucleate homogeneously, right? Our equilibrium phases, I can't do that. I have to nucleate those heterogeneously. right? So that means if I'm nucleation limited, what does that tell me about my particle size? They're going to be larger because I can't nucleate as many, so they're going to grow bigger. Where are they easiest to nucleate? Most of the time, right? Grain boundaries, right? Or dislocations or right, other heterogeneous sites. But for the most part, grain boundaries is always a safe guess, right? Are big secondary phases at grain boundaries going to give me any appreciable strengthening effect? No. Right? Right. So basically, this is what we just said. What do we need for an effective H hardening system? Solvus line curvature, homogeneous versus heterogeneous precipitation, right? And what do I mean by solvus line curvature, right? I need to be able to get an appreciable bit of solute into my system in a single phase region. If this looked like this, if this line was more straight and came up and met my my solidus line over here, and I can only put a couple atomic percent into aluminum, right? Rather than the 16 or so percent I can get into of magnesium. If I can only get 2% in, I can't make that many precipitates. So I don't get a lot of strengthening out of it. All right? So solvus line curvature is another way of saying maximum solubility in a solid state. Right? Right? And then the individual systems, right? You don't have to memorize a lot, right? I'll tend to give you as much information as that you need to know, right? I don't care, right? You do not need to memorize the precipitation sequence in aluminum zinc mag alloys, right? 7,000 series alloys, right? What is important is the general ideas of going from intermediate to equilibrium phases, right? And knowing, if you want to get real advanced, knowing that this system has a lot of potential phases in it, and so you can get your most bang for your buck in terms of H hardening out of it, right? But in general, is it going to be easier or harder to optimize your processing in this system or pure aluminum copper? There's greater gains, but it's a lot harder to do that. Right? That's generally true in life, right? Right. And then aluminum, lithium, right? Don't worry about this cellular course. Right? You'll notice I'm putting a lot less emphasis on the specific alloy systems than I am on the key sort of physical processes, right? Because if you understand the key physical processes, you can learn the details of any alloy system very easily, right? If you don't understand those key physical processes, it's all memorization for each and every different alloy system. That stinks. Okay. Right. Going back to strengthening, I meant to put the jog and dipole stuff in with the strengthening. Right. You don't need to know the details, but know that edge jogs and screw dislocations are immobile, right? So they're very effective pinning points for dislocation, right? And right, know the basics of what a dislocation dipole is, and why a structure like this would be stable. Right? Right. And then this is Hall-Petchin aluminum. Aluminum is very effective, even though the Hall-Petch line is small, because we can actually stabilize small grain boundaries. Right? Right? We can make intermetallics that have very small interfacial energies and provide grain refinement. Why is a low interfacial energy good at keeping grain boundaries small? Right? So we have solutes that segregate to a grain boundary, right? When the grain, and then they form a precipitate. And as the precipitate grows, the grain boundary energy is less around the precipitate. So if the grain boundary moves, it means the grain boundary energy is going to go up. Right? So it doesn't want to move. So even though our system can reduce energy, maybe even globally, by reducing the number of grain boundaries, we still have to get over this local energy barrier of moving the dislocation away. So we can stabilize our grain boundaries, our grains as a very small size because of that. Right? Right? So microstructure, right? So this balance between coarse intermetallics, submicron dispersions, and fine precipitates, right, is basically what the rest of this set of notes is, right? What this affects in properties, right? Generally, coarse intermetallic compounds are going to be pretty bad for properties because they're brittle, right? And are going to reduce our fracture toughness and fatigue life, right? Because they serve as crack nucleation sites. Submicron dispersions, these are potentially going to be very good for fatigue life, right? They're good for strengthening because they're going to potentially retard grain growth. But if we can get them in the interior of grains, if we can grow them homogeneously, they're going to break up our slip and prevent it from being localized on a particular slip and forming a persistent slip band. Fine precipitates, on the other hand, form the basis of our very high strength, right? But as I mentioned a couple times already, they are potentially damaging for fatigue life, right? Right? And so the rest of this slide is basically just saying that with a couple different examples. So it's pretty safe to say I might pick one of these examples and ask a question on it, right? Just like I did last year, right? With this data. Right? So maybe it's a strain hardening one. Maybe I'll pick something related on fatigue life. There's a lot of possibilities. right? But in general, it's really about the understanding of the key physical processes. And the last part was on specific alloy systems, and this chunk is the lowest. I mean, the least sort of important of stuff in terms of memorization and understanding. But you should know, at least jot down on your sheet the details, or the nomenclature. All right. Chances are I'll give you everything you need, but for a short answer, it might be useful. All right. You don't need to memorize the temper designations or the heat treatment designations. So all of this stuff you can skip over for the exam. It's here for your reference. Right? You don't need to memorize properties of the different series, right? Right. The general, I mean, all of these things basically flow from the physical mechanisms, right? So I can pick something and use it as the basis for a question, but I'm never going to ask a question along the lines of, why is 2011 aluminum good for machining and generally not weldable? Right? That's an example of a question you will never have, because that involves you first remembering that 2011 has lead and bismuth, and that's right. You have all these soft regions that break up chips and is good for, right? And then talking about why this wouldn't be good for weldability, right? Like, these are properties they're here so that you've at least seen them, but I don't care about this. All right. Something that might be of interest. All right. I could ask a question related to something like this that would say, well, I wouldn't just label it as 7000 series, right? I could potentially say aluminum, zinc, magnesium, copper alloys. Why do they generally perform better in fracture, have a higher fracture toughness than aluminum, copper, mag, right? Right? But generally, right? And ask it in such a way about iron silicon impurities, right? But I wouldn't just say, why are 7000 series generally better in fracture than 2000 series, right? Because that involves you to memorize all that stuff. I don't want that. Right? I did mention on the exam last time this T73 temper, but if you read the question, everything was in there, even if you didn't remember what the T73 question was, right? Because I had enough information talking about the different annealing temperatures, right? Below versus above the GP zone solvus, right? And it goes back to that exact same question that I had spoke about earlier. something I might give you a chart like this, right, and compare it to the chart for the 2000 series, where the 2000 series all essentially plateaued at the same stress corrosion crack velocity, but varied with respect to the stress intensity factor, versus the 7000 series, where we're much more localized with stress intensity but have different plateau rates, right? So something like that I could ask comparatively, but I wouldn't ask you ever about the crack velocity of an older alloy like 779 versus a modern alloy like 775. Right. Right. And then the cast alloys were really more for information, right? Something that might be fair game would be, as a short answer, asking about the difference between the why do you have to consider both high cycle fatigue and low cycle thermal fatigue for a cast aluminum, right? Simply because you've got the thermal cycles of an engine warming up, operating, and cooling down, right? Versus the mechanical vibrational cycles from it being a four-stroke internal combustion engine, right? But that would be, sort of a one-sentence answer there, right? The questions along these really are more, I think, better suited for Professor Lau's molten metal processing, right? Casting defects and things like that are really specific to that realm, rather than what I'm trying to get across with fundamental physical metallurgy ideas, right? If you can't relate it back to thermodynamics and mechanics, it's probably not going to be on the exam.